can send it later on. Okay. So let's start off. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum, everyone. My name is Maryam Altayeb, and today we're going to be talking about resting membrane potential. First off, I just want to preface this by saying I know you guys have your foundation exam on Sunday, but don't worry, inshallah, ya Rab, all is going to go well. And I really hope it's a good exam and that you guys have a good experience and you're very well prepared. I know it's a bit nerve-wracking considering it's your first exam in med school, but it's one of the best exams. So I hope that has a positive side to it and a negative side to it. But with that being said, let's start. And if you guys have any questions throughout the lecture, just tell me in the chat and I'll repeat anything that needs to be repeated, okay? So resting membrane potential. Let's just get the laser pointer. Okay. So resting membrane potential. First, we're going to go through the objectives. Again, stay positive, guys, and I'll explain to you why this is important today. So we're going to explain the basics of membrane potential. I'm going to talk to you guys about equilibrium potential, how these values are calculated. And then I'm going to give you a recap and question. So my lecture is two parts. This is the first part, and second part is going to talk about action potentials. That's a bit more dense, so this part is going to be, inshallah, a lot easier and a good introduction, so that once we get to action potential, we fully understand everything that's going on. So first, let's talk about excitable cells. Now, anything you do, whether it's intentional, non-intentional, breathing, moving your hands, picking up your phone, eating, whatever it is, that requires impulses. And the way that happens is by signals transmitted in the body. And those signals are transmitted through neurons or nerve cells. And I'm pretty sure you guys have learned about that already. But the important thing to know about them and what's relevant today is that these cells are excitable cells, meaning they have the capability to develop an action potential that can propagate across their plasma membrane. So basically what happens is you have a signal that starts here at the dendrites, then it goes to the body, and then it goes to the axon hillock, and then it's transmitted all the way down the nerve to whatever it is, whether it's to the muscle or whatever it may be. And this is something that goes on throughout your entire body at every single second. And it's very important for us to understand this as future doctors, inshallah, in order to understand what could go wrong, whether that's with electrolyte concentrations, which we're going to touch upon in a bit, or with nerve damage, things like that. Okay, so that's just a preface so that excitables have the capability of generating an action potential. And we have, again, nerve cells, muscle cells, and those are the main examples that we're going to talk about today. So now, first and foremost, we need to talk about membrane potentials. So just like this really cute battery here that has a positive end and a negative end. So batteries are polar, right? So it's like water. When you think of water as polar, you have a positive part and a negative part. So that's what the cell looks like. The cell is like a battery. Okay, so it's polar, it has a positive end and a negative end. And I'm going to show you an image. It's going to clarify this a bit in a second. And so what creates this positive end and negative end is the concentration of ions inside of the cell and outside of the cell. So you have, let's say, more positivity outside of the cell compared to inside of the cell at specific instances and vice versa. And so this is what creates our distinct membrane potentials. That might sound a bit confusing, but we're going to go through it here. And a lot of the pictures I included, by the way, are from osmosis. And I also included the link so you guys can see the video for it. So you have your inner environment and your outer environment of the cell. Okay, so the inner environment generally is more negative. Okay, and the outer environment is more positive. And so what creates that is a bigger concentration of negative ions inside the cell compared to outside the cell, right? And more positivity outside the cell compared to inside the cell. So what this creates is something called a membrane potential. So because you have a concentration gradient of these ions, it's like it's creating a magnet. So if you guys are into physics, which I'm assuming you're not because you're in medicine, if you ever have a circuit connected to a battery, okay, and then you put a light bulb in the middle, what's going to happen? It's going to light up because you have the flow of electrons from the negative end to the positive end. And this is what's going to create a voltage, right? Or a specific number that you'd see here on the voltmeter. And this is the exact same thing that happens inside the cell. So you have a positive end and a negative end, and it's like a magnet attracting one side to the other. So you have this magnet that's creating a voltage from one side to the other. Physics sounds good now. Well, not always. Wait, just give me a second. I can't get rid of the chat for some reason if I have a laser pointer. So I'll just put it at the bottom. Okay, so with that being said, I just want you guys to understand the concept of ionic concentrations, and you have a gradient, right? And so more negativity inside means the inside of the cell is negative, and then the outside environment is more positive, okay? And so because of this difference in charge, this is going to create a voltage or a potential, okay? Ignore the background. Perfect timing for my family to walk in. Okay. So then you have ion concentrations. And so this is exactly what we're talking about. This buildup in voltage, this potential, this energy difference or charge difference between the inside and the outside of the cell is determined by the different concentration of ions. Okay, so you have different ways of passive transport, active transport in one cell that makes this ionic difference possible. And so what determines which ions are more inside the cell versus outside the cell are two things: the semi-permeable membrane or the plasma membrane and pumps. So here we would consider the sodium-potassium ATPase that we all know and I hope love. And so what kind of ion channels can we see in a cell? You have specific channels which are ligand gated. So a ligand is a specific molecule. For example, a neurotransmitter, or if you have the NMDA receptor. We're going to talk about that a bit more in the next lecture. So these types of channels require a ligand to bind to them in order for them to open. Okay, so this is kind of like the security guard that's telling them, okay, khalas, you can pass through. You have other things that are mechanically gated, so by something like pressure. You have some channels that are always open, and these are what we consider the leaky channels, especially the potassium ones, and we're going to talk about why they're important a bit later. And so these are just always open, the channels are just present in the cell membrane. Then we have voltage-gated channels, and voltage-gated channels require a change in membrane potential. So for example, we said usually the inside is more negative and the outside is more positive. Specific things can change this gradient, and once you hit a specific value or threshold, that's going to cause it to open. If that was a bit confusing, it's okay. We're going to go over the concept a bit more later. Okay, but these are just the things you can see. So you have those that are always open, ligand gated, mechanically gated, and voltage gated. Okay. In addition, we have our active transport. Again, the sodium-potassium pump we all know and love. And we know the sodium-potassium pump always takes out 3 sodium, right? And causes 2 potassium to enter the cells. And so what this does is it has a twofold effect. One, it keeps the concentration of potassium inside the cell more high, right? And it also keeps the sodium concentration outside the cell high. Okay, that's why it's active transport. We know that diffusion is the movement of an ion from an area of high concentration to low concentration. So the sodium-potassium pump is active transport. So you're moving something from a low concentration to a high concentration. And so again, we all know that moving something against the concentration gradient is going to require energy. Okay, so when we look at these are all, or not all, but usually these are forms of passive transport. Okay, and this is active transport. Okay, and that's just revision to basic biology concepts. But until now, is everything clear? Any questions? All clear? Okay. Good. Okay, that's the easy part. So now I keep talking about these ionic concentrations, but what are they? So the 3 main ions that we're going to concentrate on are sodium, potassium, and chloride. Okay, so we already mentioned, and I already showed you in the previous pictures, you have a very high concentration of sodium outside the cell versus inside the cell, right? So you have 142 milliequivalents per liter, for example, outside of the cell of sodium, okay? But you only have 10 milliequivalents per liter inside the cell, okay? And for potassium, you have 4 milliequivalents per liter outside, but 140 inside. So just always remember, sodium is outside the cell and potassium is inside the cell. Okay, and that's going to become very important, especially later on when we start talking about action potentials. And then you have chloride. So the way I remember it is salt is sodium chloride, so they always stick together. So sodium chloride are outside the cell, more concentrated. And inside the cell, it is a lot less concentrated. Okay, so 1 second. Why are we talking about this? So I kept telling you guys about excess positive charges and excess negative charges. So when we're looking at the intracellular fluid, okay, despite having a lot of potassium inside the cell, there are a lot of negative charges from things like proteins, nucleic acids, etc., etc. So you have an excess of anions. So the inside of the cell is always negative, and the outside of the cell is always positive. And this is exactly what I was talking to you about having an electrical difference and a concentration difference, right? So this is a concentration difference because sodium is very high outside of the cell, because chloride is very high outside of the cell, and potassium is high inside of the cell. So this creates a concentration difference. Remember diffusion. So let's say this would drive potassium to go from inside of the cell out, and this would drive sodium to go from outside of the cell in, and vice versa, right? So this creates a potential, right? This is the whole topic of our lecture. This is what we're learning about. Because you have a positive charge on the outside here, the negative ions are going to want to go out. And because you have a negative charge here, the positive ions are going to want to go in. So this is what creates our potential. But what's stopping them from going in is the transporters. Either they're there, but they're not open, or they require a specific neurotransmitter, like remember the ligand-gated channels we talked about, or they require a specific voltage. Okay, and we're going to learn about that in a second. Okay, so yeah, again, just to recap, what I want you guys to know, sodium and chloride, so salt, they're always together, are more concentrated outside the cell. Potassium is more concentrated inside the cell. Okay, and the cell is more permeable to some ions in comparison to others. So for example, potassium usually can move a lot more across the plasma membrane, but other ions can't, okay? Sorry, excuse my family. Okay, so what about equilibrium potential? So this is, again, what we just talked about, but putting it into different words. So potassium has a higher concentration inside of the cell compared to outside, right? We already agreed on this. We discussed this multiple times. So this creates a concentration gradient, which is called diffusion. So potassium wants to go from inside of the cell, where it's highly concentrated, to outside of the cell, where it's not as concentrated. Okay, so this causes potassium to shift from the inside of the cell, which is very negative, to the outside. Okay, and when this happens, this creates a negative internal environment, because everything that we already said, there's more negativity inside of the cell, right? The inside of the plasma membrane is negative. Okay, so now because potassium is pushed by its concentration gradient to go outside, after a while, we already said the outside is more positive. And if you put two magnets together, if you put the positive ends together, what's going to happen? They're going to repel. Okay, that's just me. Sorry, guys. Okay, so again, to recap. First, we said potassium is more concentrated inside of the cell, right? So this concentration gradient pushes it to the outside. But now we face a problem because the outside of the cell is generally more negative. Sorry, the outside of the cell is more positive. And positive repels positive, right? So now you have this concentration gradient, or this driving force that's pushing potassium outside of the cell, okay? But then you have this electrical force that's pushing, sorry, I can't speak today, pushing potassium back into the cell, okay? So now these two differences in forces are going to create something called the diffusion potential. So the positivity outside the cell, even though potassium wants to go outside because there's a lower concentration, it's so positive that electrically it's repelling it. Okay, so the diffusion potential is going to block potassium from moving outside of the cell, even though its concentration gradient is pushing it in that direction. Does that make sense to everyone? Clear? Okay. Cool. So we said so far we're focusing on two different forces. You have your concentration gradient, okay, or that's what we're considering the chemical gradient. And then you have the electrical gradient. So when we consider the two together, that's what's going to give us our diffusion potential. Okay, so this is another way of exemplifying what we just said. So with potassium, we know potassium is more inside of the cell and it wants to go out. So that's the concentration gradient, okay? But then you have the electrostatic gradient that tells you it's a lot more positive here. Potassium doesn't want to go out. So once the amount of potassium going out of the cell is equal to the potassium going into the cell, so this is just neutral, that's what we call the equilibrium potential. And it's calculated by something called the Nernst equation. And so you have an equilibrium potential that's different for every single ion. Okay, so it's different for potassium, it's different for calcium, different for sodium, different for chloride, not chlorine. So that's the equilibrium potential for every single cell. And for it's approximately around negative 94 millivolts for potassium. Again, that's the equilibrium potential. And the way we calculate this is by an equation called the Nernst equation that we're going to talk about in a bit, although it was mentioned in your slides that you guys don't really have to know it. So again, you have different ions, and every single one of these has a different concentration gradient and electrostatic gradient. So that creates a different equilibrium potential. Okay, so you're going to have two things determining what the equilibrium potential is. First is concentration gradient, right? So moving from a high concentration inside to outside. And usually when you're losing positivity, as in potassium, that's going to give your concentration, your equilibrium potential, a negative value. Okay, so this is how I remember it. You're losing positive charges. Okay, but for, let's say, calcium and sodium, they're all, and chloride as well, they're all high outside of the cell and low inside of the cell. So when they're going to move in for the positive ions, this is what we consider a gain of positive charge. Okay, that's why the equilibrium potential is very positive. But for chloride, you're gaining it, right? Because it's going from high concentration to low concentration, but you're gaining a negative charge, right? You're not gaining positivity. I tend to exemplify here by the negative 86 millivolts. And this again is calculated by something called the Nernst equation. Okay, so again, just to recap, every ion has its own equilibrium potential, which is where the amount going out of the cell is equal to the amount going into the cell, so long as this ion is permeable, right? Or it's able to cross the cell membrane. So for potassium, it's higher inside the cell. So because it wants to go out, you're losing positive charges, meaning it has a negative equilibrium potential. As for calcium and sodium, you're gaining positive charges, meaning it has a positive equilibrium potential. And for chloride, it's going in, but you're gaining a negative charge, so it has a negative equilibrium potential. Okay, and so again, each of these is different depending on the ion that we're talking about. So now this Nernst equation that I keep talking about, what is it? Well, it's the equation that calculates the equilibrium potential. You have two versions of calculating it, depending on if the ion has a single positive charge, like sodium, or if it has a double positive charge, like calcium. So what you're going to do is you're just basically going to plug in these numbers. I'm not really going to go through the equation as well in details, to be honest. I'm not sure if Dr. Abdullah Shawaf wanted you guys to know it, like to memorize the equation or not, but you can just, 61.5 times log of the concentration of the ion outside of the cell over the concentration inside the cell. So we just know, again, potassium is higher inside, not outside. Everything else is the opposite. And that's what's going to create our equilibrium potentials. And again, chloride is a negative ion, so you're going to consider it as a negative equilibrium potential. You have to memorize it? Okay, but that's not something I can really help with, to be honest. The numbers make it here we go. The numbers make it relatively easier. This, yeah. So you guys have to memorize it. Allah ma'akum. But just make sure you know the concentrations of the ions inside versus outside of the cell. Okay? Do you guys have any questions so far? I need to stop touching my nose. Easy? Alhamdulillah. Okay. All good, guys? Okay. Yes, okay. Halas. Good. I'm just checking that you guys are still with me. Okay. So now let's recap and talk again about important terminology. We have the diffusion potential, and that's what we described in the beginning. Remember, the thing that would stop potassium from going back into the cell, even though it wants to go out. Okay, so the diffusion potential, okay, is what determines the resting membrane potential. Okay, and what determines it? One, the concentration differences for different ions, and the difference in the charges. Okay. The equation. Second part of the equation is permeability, and this is very important, so I want you guys to keep this in mind. Okay, so permeability basically means if the ion is able to cross or not. So we can consider this as conductance, or the more easily you're able to conduct, that means you have more receptors, okay, or more ion channels in the cell membrane. So we can describe it as such. Each permeable ion attempts to drive the membrane potential towards its own equilibrium potential. Okay, so that makes sense. Why does that make sense? So if you have a lot of potassium inside of the cell versus outside of the cell, when it wants to leave the cell, that means it wants to make the inside more negative, driving it towards its own equilibrium potential. Okay, and the very, very, very important principle that I always want you guys to keep in mind, and it's also going to help you a lot with action potentials, is the more permeable the ion, the more it contributes to the resting membrane potential. So the resting membrane potential of excitable cells is around -70 to -80 millivolts. And if we go back to, well, let me go back. If we go back here, we said the equilibrium potential for potassium is around -92, which of the ions is one of the closest to the resting membrane potential, right? That's relatively close to -70 or -80. And the reason that's the case is because potassium is the most permeable ion. So because it's most permeable, because remember the leaky channels I told you about, we have a lot of leaky potassium channels. So potassium contributes the most to the resting membrane potential. Okay, and so when we look at potassium that has very high permeability versus sodium that has little to no permeability, that's going to make less of a contribution. Okay, yeah, so that just explains the general concept. We said the resting membrane potential is around -70 to -80, which is close to the equilibrium potential for potassium. Why? Because at rest, the permeability of potassium is high. Okay. So just to exemplify this concept again, I just want to go to this slide. I'll go to the slide after in a second. So the conductance of potassium, which is this number here, is 0.9. So it tells you that it has a very high conductance. Because it has a very high conductance, it contributes a lot more to the resting membrane potential than the other ions. The conductance of chloride is the second highest, okay? And then you have calcium, and then you have sodium, okay? So now let's look at the different ions and why they're important. You have sodium, okay, which doesn't really have that much of an influence on the resting membrane potential. It has an influence, and I'll talk about that in a second, but it's not as significant as potassium, okay? So obviously the resting membrane potential we said is a negative number. It's not at 67, positive 67. It's closer to -70, -80, okay? And that is closest to the resting membrane potential of potassium, and it's closest to chloride, okay? So although it's closest to chloride in number, it's not super permeable in the cell membrane, so it doesn't make that much of a difference. So it's listed here because it is non-diffusible. It maintains the unequal distribution of ions. But in and of itself, chloride is not the most significant contributor. However, after potassium, it is considered significant. Okay, but what I want you guys to keep in mind is the most important ion is potassium. Why? Because conductance is very high at rest. You have a lot of leaky potassium channels that allow it to transfer from the inside of the cell to the outside of the cell. Okay, so that's one thing. Second thing is, how are we going to calculate this resting membrane potential? You're just adding up all of the Nernst equations together, right? So negative 81, which is going to be the conductance of potassium, times its equilibrium potential, added with the calcium, added with the sodium, added with the chloride, that is going to give you around negative 86 millivolts, okay? So the thing that's most permeable, I know I'm repeating it 50 million times, but again, you guys are going to get questions on this, which is why it's important. Potassium is going to contribute the most to the equilibrium potential. Then in order, potassium, then chloride, and then sodium and calcium are going to contribute the least. Okay, so the resting membrane potential is closest to the ion that is most permeable in the cell membrane. Okay, and so changing its permeability is going to change its resting potential. So just to give you guys an example, because this is very important, if you change the extracellular concentration of potassium, let's say if you add more potassium outside of the cell, which is what we call hyperkalemia, okay, or excess potassium outside the cell. So if you have more potassium here, you're already going to have a buildup of that diffusion potential that's preventing the potassium from going out. And because the potassium is staying inside the cell, that's going to build up more positive charges inside, right? So that's going to increase the resting membrane potential. You're not losing positive charges. The potassium isn't able to go outside. And so because of that, having hyperkalemia is going to depolarize or make the cell membrane more positive. So you're going to go from negative 86 to a value that's a bit more positive than that. Okay? In hypokalemia, it's going to do the exact opposite. If you have very little potassium outside the cell, it's going to want to keep going out and out and out and out. And the more positive charge you lose, right? The more potassium goes outside the cell, the more negative the resting membrane potential becomes. So this is considered, to hyperpolarize the membrane potential or make it very negative. So it's going to be, it'll go, let's say, from negative 86 to negative 19, maybe more. And again, the numbers are not exact, but that's just an example. Pretend that you guys didn't see the answer to that question. Okay. So as for this concept, do you guys have any questions? Just before I talk about the last point. Okay, so the excitability increases with hyperkalemia. Yes, it increases with hyperkalemia. And at the end of the next lecture, I'm going to talk about it a bit more in detail with a graph, but this is just a concept I want you guys to keep in mind. And the reason that happens is, remember, if you have a lot more potassium here than normal, you're not going to be able to make it leave the cell as effectively, right? Because positive charges repel each other. Okay. I'll repeat this concept. Don't worry about it. Okay. So I can draw stuff. Okay. So let's say we have, I'm on my computer, so please ignore my writing skills. So let's say we have, I'm just gonna plus this potassium, right? Let's say you have a lot of potassium outside the cell, more than normal, right? So this is what we would consider hyperkalemia. So when you have hyperkalemia or more potassium than normal outside, this potassium that's inside the cell isn't going to want to go out as much. Why? Because we said positive charges repel each other, right? It's like when you put two magnets together, then they're going to repel. If you put positive ends together and negative ends together. So that's the same concept here. The potassium doesn't want to leave the cell anymore, right? And potassium is a positive ion, right? Has a positive charge. So if it doesn't want to leave the cell, you're basically retaining positivity, or you're keeping a positive ion inside the cell. Because it's positive, what's that going to do? That's going to make the resting membrane potential from negative 86, let's say, to negative 70, or, it's going to make it more positive. Okay, or in other words, make it less negative. Okay, so that's in case of hyperkalemia. let's say you have, let me go to the eraser. Okay, let's say you have hypokalemia, right? Let's say you only have 2 potassium ions outside. There's a lot less positivity repelling the potassium, right? So the diffusion potential is not resisting the exit of potassium as much. So now potassium really wants to go outside the cell. And when it wants to go outside the cell, what happens? Remember, again, same principle, it's a positive ion. So here you're losing positive charges. And if you lose positivity, that means you're going to make this more negative. So it's going to go from negative 86 to, let's say, negative 90 or negative 95, whatever it may be. Again, the numbers aren't exact. I'm just using it so that you guys understand the concept. But most important thing, again, does that make it more clear? Then guys, is it clear? Yes, all clear. Okay, Ragad, when we get to the end of the next lecture, there's a picture that's going to explain it a bit better. Okay, so once we get there, and it'll make it a lot easier, inshallah. Okay, so just hang in there for a bit. Easier to trigger action potential, yes. But once we get to the action potential lecture, it's going to explain it a bit better. Do we need to know why it is related to excitability? Yeah, we'll get to that again once we talk about action potential. I just wanted to introduce the concept to you guys now. Okay, so last thing I want you guys to know about is the sodium-potassium pump again. So remember that what we said in the beginning. I'll use the pen again, or I'll use the laser pointer. Okay, so remember what we said in the beginning. You're losing 3 sodium ions, but you're gaining 2 potassium ions, right? So in other words, you're losing 3 positive ions and you're gaining 2 positive ions. So what's the net? It's like saying, what's 3 minus 2? That's 1, right? So you're basically losing a positive charge every time the sodium-potassium pump works, right? Because here's 3 positive charges, here's 2 positive charges. And so this helps contribute to the negativity inside the cell, right? So you're pumping out more positive than you are taking in. So this makes a very minor electrogenic contribution to the resting membrane potential. Okay, so it's just makes it a tiny bit more negative, and it's not incredibly significant. It plays a role, but it's not super, super significant. Okay, but the more important, it indirectly contributes to maintaining the concentration gradient for potassium, right? We said this is active transport. Potassium is more concentrated inside than outside, and sodium is more concentrated outside than inside. So when you're using ATP or actively pumping potassium inside the cells, this is going to maintain the concentration gradient, which is what keeps the electrical potential and voltage going across the cell. Okay, is that easy? You guys want me to re-explain anything?
Wait, so one question. The concentration of the potassium is mainly because of the sodium-potassium pump.
Naturally, the concentration of potassium is more inside of the cell, but again, the main role of the sodium-potassium pump is to keep the potassium inside, not outside. So it has 2 roles.
Is it the biggest influencing factor to the intracellular increase of potassium?
It's not the biggest, but it plays the most important role in maintaining the concentration gradient. You get me? So it has an electrogenic contribution because you're gaining 2 positive charges and you're losing 3 positive charges. So on one hand, it makes it more negative, but that contribution is very little compared to its more important role, which is making sure there's more potassium inside the cell versus
How
outside.
is there so much potassium inside of the cell, right? If there are leaky channels and the action potential causes loss of potassium. So how is the potassium so much concentrated inside if the sodium-potassium pump doesn't play?
It does play a big role, but what I'm saying saying is it plays a minor role in the resting membrane potential, like making it more negative. You get me? But the main role it plays is in maintaining the concentration gradient. So in electrically, it doesn't make it more negative by that much. It's just negative 4 millivolts. But the reason we need the sodium potassium pump is because you want to maintain the concentration gradient. You get me? So it's an indirect contribution more than it is a direct contribution. Does that answer your question?
Yeah, thank you.
Okay, Jude, what is confusing about it? Or let me draw it. Ignore sodium, ignore potassium. So if you have a cell, right? Again, ignore my handwriting, please. You're losing 3 negative charges, right? But you gain 2 positive charges. So what's the net inside? Or what's the overall inside becomes negative 1, because you basically, it's like saying you just lost a positive charge, right? Because 2 and 2 cancel out and you lost a positive charge, which makes this more negative. So what I'm saying is this is one of the roles of the sodium potassium pump. It has a minor electrogenic contribution. So it doesn't really contribute that much, okay, in terms of electricity point of view, yeah, okay? But the most important thing that the sodium potassium pump does is it makes sure that the potassium is inside the cell against the concentration gradient and that the sodium is outside the cell. And from the whole lecture we've been learning that potassium is more concentrated inside, right? Sodium is more concentrated outside. That's why this is active transport. Okay, so when you have more potassium inside, this is going to create your chemical gradient, right? So that's going to cause potassium to want to go outside by simple diffusion. Okay, and this is also going to cause a minor electrical gradient, right? Because you have more negativity inside the cell versus outside the cell, right? Because potassium, we kept talking about it, it's the most permeable ion. It's the most important in maintaining your resting membrane potential. Okay, does that answer your question? Or I hope that clears up the confusion. What's the difference between the types of gradients? Okay. So the difference between these, okay, this picture explains it best. So you have 2 different types of gradients. You have your concentration gradient and you have your electrostatic gradient. Your concentration gradient is basically what we've been learning about as diffusion ever since like we were in middle school, which is substances like to go from an area of high concentration to an area of low concentration. Okay, so that's the concentration gradient. So what's pushing it from the inside to the outside, just because of the concentration difference. When we look at the electrostatic gradient, this is looking at positive charges and negative charges. So when you have 2 positive charges next to each other, they're going to repel, right? Opposites attract. So positive and negative attract, well, positive and positive repel. So when you have a lot of buildup of positive charges inside the cell, because potassium is a positive ion, right, K plus, and the inside of the cell is already more negative, it's going to be drawn into the cell just because of the difference between positive and negative charges, even though concentration gradient is, pushing it outside. So that's why I'm telling you they work in the opposite way. Concentration gradient is going to push you outside for potassium. Electrostatic gradient is going to push you inside because you have a lot of positivity out here and it's a lot more negative in here. So once the concentration gradient and electrostatic gradient are equal, or the amount of potassium moving out is the same as the potassium moving in, this is when we call it equilibrium. So the number we calculate by the Nernst equation is your equilibrium potential. Does that explain the confusion? Jude, so the -1 is the EM. What do you mean, Judy? if you're talking about like the -1 charge, yeah, I didn't quite understand your question. Oh, so you mean like the buildup of the gradient? Okay, what I'm saying is you're getting more negative charges inside because you're losing an extra positive charge, right? You lose +3 and you gain +2. That means you have a net of -1 in here. So all that I'm saying is that the sodium-potassium pump makes a minor contribution to the resting membrane potential by making it a bit more negative, but it's not actually contributing as much as, like its main role is just to keep potassium inside the cell. That's my point. Does that answer your question? Okay. Do you guys have any more questions before I ask you a question? Okay, let's go. All right, so just again, to recap, we know cells are like batteries. They're polarized, right? Inside is more negative, outside is more positive. Resting membrane potential of excitable cells, which are nerve and muscle cells, are usually between -70 to -90 millivolts, and it's determined by concentration gradient, okay, and how permeable the ion is, and you also have your electrostatic gradient. So these are the three things that are playing a role. Does it influence the electrostatic gradient? It slightly influences it again, but it's not the primary thing that's making a difference here. Is the electrical contribution as the electrochemical force? I mean, it's the electrical driving force. You have three things. You have chemical, electrical, and electrochemical. Okay, again, I'm giving you guys just the general concept here so that you can apply it. But I'm talking about the electrical driving force. And then once you consider those two together, so again, in and out, that would be your electrochemical. So that's when you're in balance. Does that answer both of your questions? Okay. ما شفت الجواب. Okay. Basically, the resting membrane potential is maintained, and the resting membrane potential is maintained. Yes, so what restricts, okay, so the main point that you're talking about is that the resting membrane potential is maintained once you get to that equilibrium potential. So the amount in is equal to the amount out. But what's going to restrict how much an ion contributes to the resting membrane potential is how easily it can flow across the cell membrane. So if it's very permeable, like potassium, then it's going to contribute very highly, right? Because it's less restricted. The flow is easier. More ions can go outside of the cell. But you can look at it the other way, where if you have more resistance, or let's say the sodium channels mostly are closed. Some of them are open, which does make a contribution, but let's say sodium channels are closed. Because sodium channels are closed, it's not contributing as much. So it's not flowing as much from the inside of the cell, sorry, from the outside of the cell to the inside of the cell. Does that answer your question? Yeah, okay. Class, do you guys have any more questions before we go to, is the electrical force the same as the electrostatic gradient? You have, that's the way I consider it. The electrical driving force, right, is what's repelling the cells. Okay. Your electrostatic gradient, okay, is basically, it's the same way you're looking at the concentration gradient, okay? So if you have a very high concentration inside of the cell versus outside of the cell, this is going to create a driving force that pushes, let's say, potassium from inside to outside. So the concentration gradient is what creates the driving force. Similarly, your electrostatic gradient is what's going to create your electrical driving force. Okay, so if you have a lot of positivity inside and a lot of negativity, a lot of positivity and negativity inside your electrical driving force for the potassium ion to go back in. So the gradient creates the force. فهمتي عليا؟ Okay. خلاص. Any more questions, guys? I'm assuming the answer is no. I know I accidentally showed you guys the answer to this question like 5 times. سامحوني, just because I'm using my mouse. I'm not used to the scrolling feature. But we're gonna read this question anyway. So how are potassium ions moved out of a neuron when the membrane is at rest? So before you guys answer any questions, especially in the exam, just please make sure that you understand what the question is asking. Okay? So the way this question is phrased, we're talking about a neuron. So it's an excitable cell. We're talking about a resting potential. So in other words, this is asking, what direction is potassium moving during the resting membrane potential? Okay, so let's look at the options. Option A says potassium, the electrical gradient moves potassium out of the cell. Now, this doesn't make sense. If we go back to the picture that we were looking at, we know that in the electrical gradient, potassium is more positive outside, or like generally all of the ions are more positive outside. And potassium is a positive ion. So it doesn't make sense that positive wants to go towards the positive, right? So it's supposed to be the opposite, right? The electrical gradient moves potassium into the cell because inside is more negative. So A, we can exclude it completely. B, sodium-potassium pump moves potassium out of the cell. No, it does the opposite, right? I remember it as like, it pump K in, so like pumpkin, that's like same pump to go inside of the cell, not outside. So B is wrong. C, potassium ions are stable and do not move when the membrane is at rest. This doesn't make sense because potassium is in and of itself the ion that contributes most to the resting membrane potential. So C is not an option. And D is our final choice. Concentration gradients move potassium ions outside of the cell, which is true, right? Because potassium is higher inside versus outside. So it's going to want to go by simple diffusion out. And, as you guys can guess, the correct answer is D. I wanted you guys to answer it, but since I already showed the answer accidentally twice, so like, that's fine. But why is it outside and not inside? Manal, for which one? Right, for option D? Because if you look at it here, as you can tell, this is my favorite picture, but as you can see here, potassium is most concentrated inside the cell, right? Even if we look at the numbers, right? You have really high potassium inside the cell versus outside the cell. So remember, the principle of diffusion is things like to go from an area of higher concentration to an area of lower concentration. So this is the force that's pushing potassium out of the cell. Okay, so that's why option D is correct. But for the electrical force, the electrostatic gradient outside is really positive. So does it make sense to say a positive ion wants to go to the positive place? It's the opposite, right? So something positive like potassium is moving towards the negative area, which is the inside of the cell. Okay, you always get confused with the mechanism of what goes in and what goes out. So just put them as two different things. Okay, so just remember it this way. Concentration is just diffusion, what that you guys have been taking since like middle school. We all have, right? So from area of high concentration to low concentration. So that's why it's moving out. Electrostatic is the opposite. Remember, opposites attract. So positive never wants to go towards positive. Negative never wants to go towards negative. It's only positive that likes to go towards the negative, right? So here, they attract. So that's why a positive ion like potassium has a driving force, electrical driving force. So for it to go inside, why? Because inside the cell is more negative. Okay, so just separate. So concentration is one thing, electrical is another thing. Okay, does that answer your question? Good. Okay. خلاص, awesome. So, okay, don't open that. So last two things is, if you guys are still confused even after the lecture, if you should have access to the PowerPoint. They sent it on announcements, but just if you click on this, it's going to take you to a YouTube video. That's the osmosis video I referenced here, and it explains it very nicely and with nice diagrams. That's one. Second thing is, don't forget to solve the foundation mock exam. So we have the online versions. You guys can check your email and get them. They're all made by the academic aid team, and they did a really great job. And so what I like about it is it has all the questions related to your lecture. It tells you what the source is, gives you the explanation. So it's really good for you guys to practice. Even if you just want to choose one lecture topic, you can choose that topic and solve based on that. If it's really helpful, again, this is anyone who's been with me in pre-med, you guys know this code. I never change it. But again, don't be scared. You guys are getting ready for the exam now. Don't be afraid if you make mistakes. It means you're learning. You're entering your journey in medicine, so don't worry about it. If you guys have any questions, let me know in the chat. If you have any questions after the lecture, email me. This is the first one. So you guys want to take a break and restart at 5? Does that sound good for everyone? For the action potential lecture. That's going to be a bit more dense, and that's going to require a bit more of your brain power. So go take a walk, eat something, and we shall restart.
And finally, Shopify to sell your rug. So how much does it cost?
Who's shopping? Okay, خلاص guys. I'll be back in 5 minutes, okay? Okay, guys. Everyone back? Wait, let me just. Okay, خلاص. We'll send out an announcement that I'm gonna restart. Okay, you want me to explain hypo and hyper once more? حاضر. Give me just 1 second. Raghan, to answer your question. Okay. So there's 2 things you need to know to understand that question, okay, or to understand like that concept. One is that potassium is higher inside the cell, right? It's هنا مكتوبة, right? It's written here. Everything else is higher outside the cell, not inside the cell. That's one thing. Second thing is that the conductance of potassium is the highest, okay? What does that mean? It means you have a lot of channels that enable potassium to go from the inside to the outside, or basically just across the cell membrane. So potassium is the most permeable. It's the ion that can move the most out of everything else, right? So it's most easily movable across the plasma membrane, okay? So that's 2 things. So when we talked about the concentration gradient, right? You know, everything goes from high to low, okay? And that, see how thick this arrow is here? That potassium is the ion that's moving the most out of everything, where it has the most permeability, it has the most conductance, okay? Because we have something called leaky potassium channels. Okay, ignore the fact that okay? So those are the 2 things we need to know. So let's say if potassium is low, if you make it even more low, like if you have very, very, very little potassium outside, which is what we call hypokalemia, because hypo means less. What's that going to do? It's going to make it move outside of the cell even more, right? In order to maintain the balance and equilibrium, okay? And so when potassium moves outside of the cell, right, we know the inside is negative and the outside environment is positive. If you're losing a positive ion, right, if you have less positive ions inside the cell, what does that do? It makes the inside more negative because you don't have as much positive. So you're losing more negative charges. Sorry, you're losing more positive charges, which makes the inside more negative. So that's one thing. Second thing is, let's say we do the opposite. Okay, if I erase, let's say we do the opposite. Again, potassium is higher in the inside and it's lower on the outside. It has the most permeability. So let's say you have a lot more potassium outside the cell, right? So this is going to be hyperkalemia. You have more potassium. So if there's more potassium here, this force is going to be a bit weaker because it's going to say, okay, it's already high outside. Do I really need to leave that much? Okay. So if you still have more positive charges inside the cell because they're not leaving, that leads to a buildup of positive charges. So although the inside of the cell is negative, you're going to have a bit more positivity. So it's going to make it more positive or less negative. Okay, so that's why when we say hypokalemia is going to make the inside more negative, it's because you're losing potassium, because it's really low here, so it's going to keep going out, right? But in hyperkalemia, this is going to be really high, so it's not going to want to go out as much. And if it's not going out, it's stuck inside. And because it's positive, it's going to create a more positive environment inside the cell. Does that answer your question? And we'll talk about action potential now. That's like the entire next lecture. But I just want to make sure this part. I'm here for you guys. عشان أخلص lecture أروح, Right, discard the annotations. بس Ragad, did you understand what I meant about hyper and hypokalemia? I'm gonna explain it again, don't worry. بس I just want to make sure that you're following along. Okay, خلاص. Again, guys, genuinely don't be afraid to ask, and I'm here عشانكم, not for anything else. خلاص, everyone's here? Inshallah. Also, last thing, guys, don't be afraid to unmute. Like if I ask you something hard, just answer. Okay, so now we move on to part 2, which is learning about the action potential. Okay, there are some concepts that are a bit more complicated, but inshallah we're going to try to make it as easy as possible. Again, any questions you have, please tell me. These are the objectives, just so you guys have as a reference. Okay, so now just to revise over what we just talked about in the previous lecture. Resting membrane potential. We know that you have different concentration of ions inside the cell versus outside the cell, right? And this leads to distinct membrane potentials, okay? And the concentration gradient is determined by positively and negatively charged ions, right? And because there's a difference inside and outside the cell, this creates a buildup of voltage or our potential, right? So that's what membrane potential is. And you have excitable cells that are capable of making action potentials and transmitting them across, like muscle cells and nerve cells, okay? And so again, this is the same image that I used, same slide in the previous one. So you have a more negative internal environment and a more positive external environment. And this difference in charges creates a voltage, right? Like a voltmeter if you attach it to like a battery. Okay, so this creates a voltage, which is what gives us our resting membrane potential. Okay, so this is just a recap of everything we just said. So now when we talk about action potentials, I already told you guys in the beginning of the lecture that everything in our body needs information in order for that to happen. And then action potential is one of the ways that we transmit that information in our body, specifically through the nerves. SubhanAllah, if you just think of something like, let's say I want to raise my hand, I needed an action potential to go from my brain to tell my muscle to contract in order for this movement to happen. And so this happens very seamlessly, SubhanAllah, in the body. And it's very important for us to understand in medicine, because any problems with transmitting this information can lead to, let's say, different issues in the body, whether nerve damage, muscle damage, abnormalities in the heart, which we call arrhythmias, etc., etc. Okay, so that's what an action potential is. And the interesting thing about action potential is that it's kind of like a domino effect. So you have opening of voltage gated sodium channels that we're going to talk about in a second. And then once it opens, let's say at this part of the neuron, it's just going to keep transmitting all the way down until it reaches its target, for example, the muscle cell. Okay. So that's what an action potential is. Now, how do action potentials happen? Let's say a friend tapped you on the shoulder, right? If they tap you really lightly, you might not even notice it. You might not feel it. But if I come and I punch you on the shoulder, you're definitely going to feel it. So the key thing here is if a stimulus is strong enough, right? It's strong enough, then an action potential will happen. Okay. Again, if your friend taps you really lightly, you might not even feel it. But if they tap you really hard, you're going to feel it. So the stimulus now is stronger, which is going to make sure that that action potential happens. You cross something called the threshold, or the minimum value required for an action potential to happen. Okay, so once an action potential does happen, what do we see? We said the inside of the cell is negative, right? Like a magnet. So the inside of the cell is negative. And once those voltage gated sodium channels open, what's going to happen? Negative attracts positive, right? And sodium is a positive ion. So it's going to rush into the cell, and that's going to cause an action potential. So let's look at this again. I want you guys to make sure you understand these terms because it's going to make your lives a lot easier, one. And it's going to make sure you're being asked, okay? Remember how we said the cell is polar? It's like a battery. Remember that stay positive battery that I included in the beginning? So the cell is polar, right? Has a positive end on the outside and a negative end on the inside, okay? So when I tell you I'm depolarizing the cell, the prefix D means to remove. So to remove polarization. So that means you're making it less negative, okay? Just to go over these terms. So when you're depolarizing the cell, there is an influx of positive ions, which makes it less negative, okay? If you're repolarizing the cell, well, re means again. So repolarization means to make the cell polar again, okay? So when you're making the cell polar again, that means you're making the membrane potential more negative, okay? So depolarization, which we'll see in a second, is the upstroke. Repolarization is the downstroke, okay? When you say hyperpolarization, hyper means extra, a lot, more than normal. So hyperpolarization means you're making the resting membrane potential or the membrane potential even more negative than the normal. So hyper, it's like it's more than normal, right? So you're making it more negative than normal, okay? And so last key term that I want you guys to know is the threshold potential. So if you think of a door, okay, you're either inside the room, outside the room, okay? So the threshold is the membrane potential at which an action potential must occur. If you reach this value, no matter what you do, an action potential is going to happen. You know, so it's like if you, let's say, touched a fire, okay, by accident. You either felt it or you didn't, right? So your membrane potential reached a specific value, which is the threshold, and then an action potential occurred. Immediately, what are you going to do? You're going to draw your hand back, right? That's because that's sending a signal to your body that, hey, okay, I touched something dangerous, okay? So again, just to recap, when you're depolarizing the cell, that means you're making the inside less negative. Remember, D means to remove. Polarization, we're talking about the negative charge inside. So you're removing the negative charge, i.e. making it more positive. Repolarization means to make it negative again, okay? Hyperpolarization means to make it even more negative than normal, which is more negative than the resting membrane potential. And then the threshold potential is the membrane potential at which either your action potential happens or it doesn't. There's no in between. And an important principle that comes with this is that your action potential either happens or it doesn't. It's all or none, okay? So again, all or none. The action potential either happens or it doesn't. You can tell me this door is open, this door is closed. Like there's no like midway between the two, okay? Is that clear so far for everyone? You guys can unmute and tell me. I feel like I'm alone. I haven't been on Zoom in so long.
Yes.
Listen, you just tell me. If you guys have any questions, just let me know. Yes? Okay. Alhamdulillah. So now let's go back to the ion channels. I told you guys that we have ligand-gated channels and leaky channels and voltage-gated channels, right? So the two that I want to focus on right now are the ligand-gated and the voltage-gated, okay? Why are we talking about the ligand-gated channels? Well, we said basically from recap from last lecture, when a neurotransmitter or a specific chemical binds to them, they open, right? And if the chemical isn't there, it's closed. Okay, so this is, for example, the NMDA receptor that you can find in the brain. And then you have voltage-gated channels. Remember, the voltage-gated sodium channel is the primary thing we're going to be talking about in the action potential today. And so what it needs a specific stimulus. It needs a change in the membrane potential that we've been talking about for like an hour now. Okay, and once this membrane potential changes, and remember, when it reaches a specific threshold, when it reaches that value, like the door that's open or closed, Once you reach that value, خلاص, action potential is going to happen. Why? Because these voltage gated channels are going to open. Okay, so now it's open. So sodium, tell me, from inside to outside or outside to inside? Now, guys, where does sodium go? Outside to inside. Exactly. Because sodium is more concentrated on the outside of the cell. So the gradient is going to push it into the cell. But what is it waiting for? It's waiting for this gate to open. Okay, so the voltage gated sodium channels. So now we have specific graded potentials. Okay, so when we talk about a graded potential, same way, so again, going back to the example that I told you about, if your friend taps you on the shoulder and you don't feel it, okay, that means the stimulus is not strong enough. When we talk about a stimulus being strong enough, okay, so what that does is you have a tiny, tiny, tiny bunch of stimuli, right? And so if this is the stimulus, for example, and it goes to the synaptic terminal, or this is the nerve, and then the cell body, if it's strong enough, that means you're going to cross the threshold. Okay, so this, for example, is a stimulus that crossed the threshold. Okay, and then it's not going to stay in one specific spot, right? It needs to travel all the way to the axon. Hey, look here, and then it's actually going to transmit the action potential. So think of it like an echo, right? Or let's say you're yelling at your sibling to like get you something. And from the point where you're standing to like, let's say all the way across the room, by the time, let's say if you whisper to them, hey, get me a glass of water, they're not going to hear you, right? But if you're going to yell it at them, if the stimulus is stronger, oops. So by the time it gets to the trigger zone here, it's still going to be above the threshold. I hope you guys understood my analogy. But the point I'm trying to come across here is if the stimulus is weak, that means once it gets to the trigger zone, to the point where it's actually supposed to be above the threshold, okay, because the stimulus is weak, you lost a lot of its strength by the time you got here, and then it's not going to cause an action potential. Okay, so this is what we call a sub-threshold graded potential. So over time, it's not strong enough to cause an action potential to happen. Okay, but when you look at the supra-threshold graded potential, this is like when you yell at your sibling to get water for you or to do whatever. So the stimulus is very strong in the beginning, so that even though it's going to decrease in magnitude a bit, as you can see here, once it gets to this trigger zone, once it gets to the axon hillock, it's still above the threshold. So this means your action potential is going to happen, and it's going to happen. Again, remember, it's all or none. So supra threshold means you're above the threshold. So that means no matter what you do, action potential happens, right? All or none. If it's sub threshold, okay, that means it didn't quite reach that value that you needed to reach. So this is the whisper example, you get me? So once it gets here, the action potential doesn't happen. Okay. Easy enough. So super threshold passes the threshold, action potential happens. Sub-threshold, weak stimulus, not strong enough. Can you give an example that happens in the body? Example that happens in the body. Well, the best example I can give is, again, using your, let's say, your hands as a stimulus, because that's the easiest. I mean, it's a bit more complex of an example, so I don't want to use it to confuse you guys. But let's say let's say you're hearing, right? So there's always like a type of hearing test that sometimes you do where you like rub your fingers together and you see how far apart you can get, how far your fingers can get until you can still hear it. So this, let's say, if it's really far and you can't hear it, you can consider that sub-threshold because your stimulus is not strong enough. But super threshold would be really close. Again, not the best example that I can give. This, I would much prefer the shoulder tapping example. But okay. Will the stimulus always be external? You can have neurotransmitters that submit. That in and of itself is like a stimulus for the action potential to go. Like let's say you think, I want to raise my hand. That's something that's going from top to bottom, not necessarily down to up. You get me? So that's another example. We're just quantifying the stimulus is much easier if you look at it externally than internally. I hope that answers your question, Noor. But otherwise, okay, you guys said all good. So now we have something called the length constant. To be honest, I wasn't going to include this for you guys, but good, just in case he asks a question. So when we talked about this, right, your graded potential is always going to decay. It's always going to get weaker the further you go, right? Like if I yell into someone's ear is different than me yelling at them when they're across the room. It gets weaker as you go, like with time or with distance. So it's the same principle here with the length constant. So a graded potential will decay the further away it gets from the origin. Okay, and the reason this happens is because you have ions that leak out of the cell membrane. Okay, so let's say this is your example here. So at the point of origin here, it's going to be strongest. And then as you go further away in terms of distance, it's going to get weaker. Okay, so again, yelling at your siblings. I'm so sorry for like any siblings that are being yelled at the moment, but that's just like the best example I can think of. So then at this point, you have something called the length constant. So it's basically the distance where you have a decrease, 37% decrease of the original amplitude of your potential, graded potential. So what that means is basically, we said this is the origin point, right? This is where it's strongest. So when it decreases 37%, that's what's going to determine your length constant. So how far did it need to go to decrease by 37%? Okay, and basically the point of this example is just telling you if you have less ions leaking out, okay, which means your membrane is more resistant, it's more rigid, it's not letting the ions leak out as much, okay, then your graded potential is going to be stronger, which means you have a larger length constant. And to be honest, I didn't really see the need to explain this concept. Again, I just said I'd include it in case the doctor wants to ask about it. But again, so just by principle, graded potential decays the further away it travels from its site of origin. We quantify that by the length constant. Okay, and what determines the length constant is how much ions are leaking out of the membrane, right? So the more resistant it is to leakage, the bigger the length constant, the more able the nerve is to carry a signal across, to the axon hillock and then have an action potential. It's used for what and when? Well, there are some specific diseases that you guys are going to learn about later, very advanced, like for your stage now, where you have demyelination of your peripheral nerves, and you have increased resistance in the cells, which would increase the length constant. Well, again, صراحة, I didn't want to explain it. I just said I'd include it in case an MCQ comes about it. But yeah, so that's just the general concept. Again, not my favorite thing. What's more important for me and what is more important for the action potential concept in general are the properties of action potentials. So we said already depolarization. So we know again, D means to remove and polarized means the negative charge inside the cell. So to remove the negative charge inside the cell, that's depolarization. And so we know action potentials are initiated by depolarization at the axon hillock. Okay, we already talked about this. Action potential is all or none. Either happens or it doesn't. Okay, threshold voltage is usually 15 millivolts to the resting membrane potential. So if your resting membrane potential is -50, usually, but not always, your threshold is going to be, let's say, 35. Okay, and last thing, and this is important because they get you MCQs about it all the time, and the concept can be a bit confusing. Action potentials have a constant amplitude. And so what that means is, okay, let's say this is the example. So remember how we said there's going to be a graded potential. So it's going to get increased until it hits the threshold, right? So this would be sub-threshold. This is supra-threshold. No matter how strong the stimulus is, so long as you're going to have an action potential, okay? And every single action potential looks the same. In every nerve in your body, every excitable cell, your action potential is going to have the same type of graph in that respective cell type. So what this means is that action potentials do not summate. So action potentials aren't like graded potentials. So graded is, let's say, here's the stimulus, it's getting stronger. So a lot of graded potentials can come together, okay? And then so long as it crosses the threshold, then you have an action potential. But every single action potential looks the same. So you can't say this action potential is stronger than this one and this one is weaker. No, they all look the same. So how can the body tell the difference between an action potential, or let's say a lot of action potentials happening and a lot less action potentials happening? Or in other words, how can the body tell me that, okay, the stimulus is much stronger? So the way it does that is by the frequency of action potentials. You're not going to have with a stimulus this strong, for example, the action potential looks the same as this stimulus, even though it's much weaker. But what's going to make a difference is how many action potentials you have, okay? So the information is coded by frequency, or how many action potentials you have, not how big the action potential is, because the amplitude is always constant. It always looks the same, okay? Just want to make sure you guys get that, because they get it in questions a lot. So remember that action potentials, depolarization at the axon hillock, okay? All or none, so either happens or it doesn't. You just need to cross the threshold. All action potentials look the same. What determines the information coded is how many action potentials you have, not how physically big the action potential is, because the amplitude is constant. I really need to figure out how to use my mouse properly. Okay, anyway, do you guys understand the concept generally?
Yeah.
Are you still with me?
Yes.
Okay, خلاص. Thank you. بس عشان النفسية. بس okay, خلاص. Cool. Amplitude looks the same in all stages. It looks the same for a full action potential. We're going to look at the stages in a second. But what they're saying is basically the millivolts, or like the voltage that your action potential reaches, is always the same. It's not فجأة going to reach like positive 90 millivolts or suddenly negative 70. They're all like approximately at the same point. Even in hyperpolarized, I'm talking about one full action potential. No, I'm not talking about the stages of action potential. We didn't get there yet. That's the next topic. As I'm saying, the amplitude of one full action potential is always the same. It's always constant. And if you have 50 action potentials next to each other, they're all going to look the same. But what's going to make a difference is how many action potentials you see. If you see like 3, that's going to tell you, okay, this is like a weak or stimulus versus like 50. That's going to tell you, okay, this is a very strong stimulus. You get my point? Okay. Any questions? We got through the bulk of it. Now we just have the actual action potential. Okay, so if you guys don't have any questions, well, I really need to stop doing that. Okay, well, let's get going. So now we get to the good stuff, which is the phases of an action potential. Okay, so this is what you were asking about, Noor. Again, when I'm talking about amplitude, I'm talking about this, how high it goes up and then it goes down, okay? So we have different phases of the action potential. I just want you guys to get a general look, and then we're going to take each part separately, and then we're going to understand how this happens, okay? So first, we have our threshold potential. Okay, so when we're talking about the threshold potential, or the resting potential here, so the RMP, we already know what's the main ion. Can you guys tell me, like unmute or tell me in the chat? So that was basically the entire lecture that we took just now. Potassium. Thank you, Maryam. Yeah. Perfect. So the main ion that determines resting potential is potassium. Can anyone tell me why?
Because it's
Pretend like
intercellular.
It has a high permeability.
exactly. It has the highest permeability. And it has the highest permeability because of the presence of leaky potassium channels in the cell membrane. Remember, the leaky channels are the ones that are always open, and we mostly have them for potassium. Okay, so that's why at rest, we know the cell inside is more negative, out more positive, and the resting membrane potential of potassium is around negative 94. And so for normal cells, the resting membrane potential is around negative. Yeah, no, conductance also means permeability, yes. So the more permeable an ion is, the more you're able to conduct it, okay? So making the membrane potential approximately negative 70 millivolts, okay? Because the main phase, the main ion of the first phase or the resting phase is potassium, okay? One thing I want you guys to keep in mind, and this is an MCQ I have for you later, so I'm giving you a cheat sheet a bit, but right, it's not negative 94 like potassium. The reason for the very slight difference is because you also have sodium channels that are open. Again, they're not as permeable as potassium. Potassium is the main one, but just keep that in mind also, okay? That could be a tricky concept. But again, if you guys didn't get it the first time, I'm going to repeat it like 5 more times, so don't worry. Membrane potential. So these are our voltage gated channels. Remember, these open with a threshold potential, like after you cross it. Hello. And so right now, sodium channels are closed. Sodium has a few channels as well, but again, we'll get to that next. I just want you guys to know that resting membrane potential is negative 70, not negative 94. But potassium determines the resting membrane potential the most because its conductance is higher. I'll explain the other concept in a bit, but just stick with me, okay? Okay. Did I miss a slide? Well, wait, no, this is the. Okay, I don't. You guys should be able to see my PowerPoint slide. Okay, yeah, sure. So now we get to depolarization. We already talked about the action potential being all or none. So you cross the threshold around, your action potential is always going to happen. It's all or none, okay? Either happens or it doesn't happen. If you have a super millivolts, then no matter what you do, an action potential is going to happen. Okay, so what happened here is you have a opening of the voltage gated sodium channels. Okay, remember voltage gated means it needs a specific amount of voltage. Okay, you need more positive membrane potential, then it's going to open. Okay, so now we're in this phase, which is here. What happens is you're depolarizing the cell. We already talked about the means to remove polarity, or you're making the inside more positive, right? So what happens? You have the opening of the voltage gated sodium channels right here, okay? And is sodium more concentrated inside the cell or outside the cell? Can you guys tell me? Outside the cell. So is it gonna go in or is it gonna go out?
In.
It's gonna go into the cell, exactly, for two reasons. One, concentration gradient. Second, electric gradient, right? It's negative inside the cell, so the positive charge is going to really rush into the cell. So that's what we call a fast inward positive current, making the cell interior more positive, okay? So why is it sodium? Because the threshold potential is where you have the opening of the voltage gated sodium channels. Okay, easy enough. Okay, that was a hypothetical question, but I was assuming the answer is yes. Other than just a positive than zero. Okay, so when you have your threshold hit, this is what we call the upstroke. See how it's going upwards? It's becoming more positive, positive, positive. This is because all of those sodium ions are rushing into the cell. So now the inside of the cell is more positive, right? Sodium is a positive ion. So you're bringing all of those plus signs, you're bringing all of those positive signs inside the cell. Okay, so this is what we're calling the upstroke. This is the depolarization phase. And this happens again because you have opening of the voltage gated sodium channels. Why do the voltage gated sodium channels open? Because you pass the threshold potential. This is like the gate. This is the voltage you have to reach in order for this to happen. Okay, so sodium flows in for two reasons. One, because its concentration gradient is more outside than inside. Okay, and two, because it's more negative inside the cell. So those two things are the driving force for sodium to go inside. Okay, the reason this doesn't happen to potassium is that potassium channels are not open at this point. Potassium channels, the voltage gate, although potassium is permeable because you have the leaky channels, it's not enough for like potassium to leave the cell in the same amount as sodium going into the cell. You guys understand the depolarization phase so far? Yes.
Yes.
خلاص. So now there's a really important a lot at this point. Once here, why does sodium stop entering? Like, why does it go back down? Why doesn't it just continue entering? That's because at positive 30 millivolts here, you have something called the inactivation gate. So you see this kind of like ball and chain looking thing here. So the inactivation gate closes at positive 30 millivolts. So what this does is it blocks the channel and we can enter. So this was basically the first phase where we're resting. Once you reach the threshold, it becomes open, right? So here's where the depolarization happens and sodium enters the cell. And then once you get to about positive 30, so the tip of the upstroke there, that's when you have the inactivation gate blocking the channel. And so no matter what you do, even though it's technically open from here, it's just preventing all of the sodium ions from rushing in. Okay, so that's why sodium doesn't continue to enter, because of the closure of the inactivation gate. Okay, so now we move to repolarization. Okay, and with repolarization, again, let's just think of it in definition terms because that makes it easier. Re means again, polarize means to make negative, right? So to make it negative again, to make the resting membrane potential negative again. Okay, and so what happens is at this point, right, we said the inactivation gates of sodium closed, sodium channels. Okay, we have the opening of the voltage gated potassium channels. And when the voltage gated potassium channels open, which are here, see, inactivation gate is closed, potassium channels are open. And now there's a lot of positive charge inside the cell, right? Because there's a lot of sodium inside the cell. And potassium is more concentrated, again, inside or outside?
Inside.
Inside the cell. So does it want to go into out or out to in? It's going to go outwards. And now you have two driving forces. You have one, the fact that it's a lot more positive repels positive. Two, the concentration gradient pushes potassium to really move outside and do that very quickly. And that's why the voltage potassium. Okay, so here the conductance of potassium is the highest. So at this point, bring this up to go the opposite direction. At which stage does EPSP and IPSP start contributing? Just go through, okay? Is the potassium pulling the membrane potential from or عادي يعني you can unmute and ask برضه, it's fine. Okay, so I'm gonna continue by the time you rephrase your question. Okay, so that's when we did, okay, so we depolarized the cell, right? We repolarized it, so now we reach the resting membrane potential again. And now we're going to hyperpolarize it, okay? So hyper means more than normal, right? So hyperpolarized, so making it more negative than the resting membrane potential, okay? So more negative than the resting membrane potential. And so that the problem is generally we have these potassium channels, right? But they close very slowly. So although now we reach the resting membrane potential again, slower close, which leads to even more potassium leaving than normal. And so because of that, that causes it to be more, which is why we consider this hyperpolarization. Just basically just happens because the ions are so that's for hyperpolarization, okay? And now how do we get back to resting membrane potential? Remember, sodium-potassium pump is very important in maintaining the concentration gradients. So all the potassium that left and all the sodium that's inside is going to be kicked out and brought back in. So K is going to be pumped in, sodium is going to be kicked out by the what do you call it? By the sodium-potassium pump. Okay, so that's going to basically bring us back to the resting membrane potential. At this point now, sodium channel is closed, voltage-gated sodium channel is closed, voltage-gated potassium channel is closed, and now we're back to resting potential, where another action potential can happen. Okay, so, okay, do the question. Multiple cycles will look the same as this. Yes, exactly. So that's what I wanted to tell you guys. Every single action potential is going to look like this. Okay, every single action potential is going to have the same amplitude. Okay, but again, the way the body transformation is not how large or how big the action potential is. It's how many action potentials you have. If you have like and then another one, that's not the same signal as if you have like 5 action potentials stuck together. You get me? So that's the key concept there. Or should we go into a more complicated process? So what's the complicated process, Jude? Tell me. And maybe the questions, when I get you guys the questions, you'll see what I mean. Okay. Do you guys have any questions about the action potential itself? Easy. Does the magnitude of the threshold matter? Will it affect the amplitude? No. The magnitude of the threshold, if you get here, if you get to -50, if you get to the threshold, that's this is what you need in terms of like the magnitude of the stimulus. So long as the stimulus gets you past 50, inshallah it's 51, this is like read because your action potential is always going to look the same. Okay, I'm going to talk about the refractory periods right now. But again, as long as you cross the threshold, your action potential is always going to look the same. What makes a difference is how many action potentials you have, not what they look like. Super threshold and sub threshold. Okay. I'll get to that in a second. Okay, so if you have a stimulus, okay, let's say it's a weak stimulus. In the longer, and then again, my example, if you're whispering to your sister or your brother or whoever across the room to do something, because you're whispering, whatever you said, by the time it gets to them, it's going to be really weak, right? But if you scream something across the room, okay, maybe it might not be as loud as the stimulus is weak. So let's say you're whispering. By the time it gets across the cell or across the room, it's going to be really weak. So they're not going to be able to hear it, or it's not strong enough to trigger an action potential. It does not get past the threshold at the axon hillock here. Okay. But if you have a stimulus that's a lot stronger, that means even though its strength is going to decrease as it gets, let's say, across the room or across the cell body, even though it's weaker, once it gets here, it's still strong enough for, let's say, the person to hear it, or it's still strong enough for, it's still past the threshold once it reaches the trigger zone or the axon hillock. So that means it's going to cause an action potential. But if it's very weak, meaning it's sub or below the threshold, it's not going to cause an action potential. Okay, so that's the sub-threshold graded potential and the supra-threshold graded potential. And so when you asked, okay, so Faisal, when you asked about the EPSPs and the IPSPs, so the EPSPs, this is what it is. So when you have excitatory potentials, okay, so that's basically the stimuli. Okay, so and that's mediated by sodium. But if you have something inhibitory, that's mediated by chloride, not sodium, because chloride going in is going to make the inside more negative. Sodium is going to make it more positive. So that's basically the idea of that. So here, again, just to reiterate, the stronger the stimulus is, okay, if it crosses the threshold, no matter what you do, the action potential is going to happen. Concept. Now, most important thing I want you guys to keep in mind, get here in the middle of our action potential. Once we get here, we set the inactivation gates of sodium close. So let's say you have a very strong stimulus and let's say you keep poking your sister, right, on the shoulder. Okay. If you happen to stimulate at this time where the inactivation gate of sodium is closed, no matter what you do, no matter how strong the stimulus is, it will never create an potential. Why? Because this isn't activated. The inactivation gate is closing. It's blocking the sodium from moving in. So no matter what you do, it's not going to